Slide 1. Electrophysiology of the Heart is a series of slide tape programs developed and produced by the American Physiological Society. This is Electrocardiography, Fundamental Theory, Part 1. Content expert, Dr. Morton F. Arnsdorf. 2. Electrocardiography is the study and interpretation of the electrical activity of the heart as evidenced by measurable potentials on the surface of the body. The record of the variations in magnitude and polarity of potentials caused by cardiac electrical activity is called an electrocardiogram, or ECG. All normal and abnormal deflections displayed on the ECG depend on current flow across cell membranes, between groups of cells, and through the electrolyte-containing volume conductor that is the human thorax. 3. In fundamental theory, we will consider the relationship between the electrical activity of the heart and the electrical perspective from which it is viewed in terms of two theoretical frameworks. In Part 1, we will discuss the distributed dipole model and solid angle theory. In Part 2, we will discuss the classical single dipole model and the equivalent vector concept. This is not a course in clinical electrocardiography, but rather an introduction to concepts useful in the interpretation of the electrocardiogram. 4. Questions and answers are provided throughout this program to allow you to assess your readiness for the program, your progress during development of the concepts, and finally, your overall comprehension of the material presented. After a question is stated, you must stop the tape while you formulate your answer. Many of these answers require you to make rough sketches or simple drawings. After an answer is explained, you must stop the tape to assess your response. Of course, you should also stop the tape whenever you want to study the visual material. The prerequisite test begins on the next slide. 5. Is the interior of a quiescent cardiac cell negative or positive with respect to the exterior? Is the resting transmembrane voltage determined primarily by the relationship of extracellular to intracellular concentrations, or more properly activities, of potassium, sodium, chloride, or calcium? 6. The interior of the resting cardiac cell is negative with respect to the exterior. The resting transmembrane voltage, V sub R, is determined primarily by the ratio of extracellular to intracellular potassium concentrations or activities. The resting cell membrane is a dielectric and acts as a capacitor in maintaining separation of charge and storing charge. Energy-requiring ionic pumps maintain the appropriate intracellular and extracellular potassium concentrations, and V sub R approximates the potassium equilibrium potential, EK. 7. Indicate whether the interior of the cardiac cell is negative or positive with respect to the exterior at the peak of regenerative depolarization. At threshold, does regenerative depolarization result from increased membrane conductance to potassium, sodium, chloride, or calcium? 8. At the peak of regenerative depolarization, the interior of the cardiac cell is positive with respect to the exterior. This is due to a voltage-dependent increase in sodium conductance at threshold and the inrush of sodium ions down the concentration gradient. The peak of the overshoot approaches the equilibrium potential, ENA, for sodium, which is about plus 40 millivolts. 9. Make a sketch of this cardiac cell. Indicate the approximate resting potential and peak overshoot potential. Indicate the wave front of activation and the direction of action potential conduction. 10. The boundary between the resting and excited tissue is the wave front, and the direction of conduction is from left to right. If you are not familiar with these prerequisite concepts, study the bioelectrical properties of excitable tissues and action potential propagation in the introductory slide tapes in this series. 11. In this program, we will discuss the electrical properties of a dipole layer, and the activation wavefront boundary, the spatial and non-spatial determinants of potentials recorded by the electrocardiograph, and some applications of the distributed dipole model and solid angle analysis and its advantages and limitations. 12. Your first objective is to be able to describe the electrical behavior of a single dipole and a distributed dipole layer, and to describe the polarity and movement of a wavefront boundary. 13. A dipole consists of two equal but opposite charges held a short distance apart. 14. A dipole in a conducting medium is in essence an electrical generator. Positive charges flow along lines of force from the positive pole, the source, to the negative pole, the sink, creating a current. 15. An electrical field is established in which the distribution of potential may be described by isopotential lines perpendicular to the lines of current flow. For example, the potentials detected by electrodes at sites P1 and P2 will be identical positive potentials. The potential detected at site P3 will be negative. No potential will be detected at site P4. It is in the plane perpendicular to the center of the dipole axis, the plane of zero potential. 16. When a membrane of finite thickness separates positive and negative charges, a membrane dipole layer is formed. 17. The cardiac cell maintains a separation of ionic charge between intra- and extracellular fluid, and therefore may be said to be surrounded by a membrane dipole layer. In the resting cardiac cell, the interior of the cell is about 90 millivolts negative to the exterior. Note that in maintaining separation of ionic charge, the resting cardiac cell membrane acts as a capacitor, and since the membrane has a relatively uniform dielectric constant and thickness, the amount of charge stored per unit of membrane surface area is proportional to the transmembrane voltage. 18. When the threshold for regenerative depolarization is attained, sodium conductance increases and sodium ions rush into the cell, producing a relative intracellular positivity with the transmembrane voltage reaching plus 40 millivolts at the height of the action potential. Positive ions, primarily potassium, flow through and between cells from the area of relative positivity to areas having more negative potentials, such as the resting segment. Potassium flows from the interior of the cell through the membrane to the extracellular volume conductor, thereby completing the local current circuit. 19. The change in transmembrane voltage during regenerative depolarization alters the polarity of the membrane dipoles in the activated region. The juxtaposition of resting and excited tissues produces a separation of charge over a finite distance at the membrane surface. This separation is called a boundary. 20. The separation of charge at the membrane surface creates a distributed dipole layer composed of an infinite number of dipoles representing infinitely small portions of the boundary. 21. It is these surface dipoles that are of importance to the extracellular potential and the electrocardiographic record. They are the source of extracellular current flow across the boundary and throughout the surrounding volume conductor that is the human thorax. 22. As in the model of a single dipole, the distribution of potential in the electrical field established by a distributed dipole is represented by isopotential lines perpendicular to the lines of current flow. 23. We have seen then that a totally quiescent cell, while maintaining a stable transmembrane voltage, generates no detectable extracellular potentials. Only a boundary between activated and resting regions will produce the surface distributed dipoles that establish extracellular current flow and the development of a potential distribution throughout the thorax that can be recorded electrocardiographically. 24. The polarity of the potential detected at an electrode site and recorded by the electrocardiograph depends on the orientation of the boundary toward the electrode. In this example, the magnitude and polarity of the voltage are recorded as the boundary moves from left to right. The zero potential is indicated by the disk at right angles to the boundary. By convention, when the boundary moves toward an electrode, a positive or upward voltage deflection is observed in the ECG. Note that the magnitude of the deflection increases rapidly as the wave front approaches the electrode. 25. When the boundary is oriented so that the electrode is perpendicular to the dipole axes, the electrode is in the plane of zero potential and zero voltage is recorded. Note the rapid decrease to zero in the ECG. 26. When the boundary moves away from the electrode, a negative or downward voltage deflection is observed. The magnitude of the deflection increases sharply and then decreases. Remember that the polarity of the ECG depends on the orientation of the boundary toward the electrode. 27. Sketch a dipole with this spatial orientation and draw several current flow lines showing the direction of flow. Draw several isopotential field lines and state the polarity of potentials detected at the 3 electrode recording sites indicated. 28. The potential detected at P1 would be positive, at P2 negative, and at P3 zero potential would be detected since it is in the plane perpendicular to the 0 point of the dipole axis. 29. In this diagram, conduction is from left to right. Draw the net local current circuit responsible for the separation of charge at the boundary. What are the transmembrane voltages of the interior of the cell with respect to the exterior of the cell on each side of the boundary? Sketch the relative magnitude and polarity of the voltage recorded at site P during movement of the boundary past that point. 30. The directions of local current circuit are shown. The interior of the cell is 40 millivolts positive to the exterior during the peak of the action potential, and 90 millivolts negative in the resting state. The potential recorded at point P increases to a peak, falls sharply to zero, falls to a negative deflection, and returns to zero. 31. Your second objective is to be able to identify and interpret examples of spatial and non-spatial determinants of recorded electrocardiographic potentials. 32. Theoretically, the extracellular potential, E, recorded at an electrode site is equal to the product of the ratio of the solid angle, omega, to its maximum value, 4 pi, the difference in the transmembrane voltage across the boundary, Vm2 minus Vm1, and a conductivity term, C sigma. These terms reflect the influence of spatial and non-spatial factors on the voltage recorded by the electrocardiograph and will be discussed in turn. 33. We have shown that in the distributed dipole layer model, a difference in transmembrane voltage between two areas creates a separation of charge referred to as a boundary. The apparent geometry of the boundary can be described by drawing radii from a point P to all points on the boundary, forming a cone. 34. To measure the geometry of the boundary, a unit sphere is inscribed about point P. The area on the surface of the sphere cut off or subtended by the cone is termed the solid angle, omega. 35. The solid angle is geometric and therefore reflects the influence of spatial factors on the potential recorded by the electrocardiograph. Omega depends on the distance between the boundary and the recording electrode and on the geometry of the boundary. 36. In this example, the distance from the boundary to the electrode site is constant, but the extent of the boundary on the left is clearly greater than that of the one on the right. This is reflected by the larger solid angle, omega 1, as compared to omega 2. 37. The recorded deflection will be greater for the boundary that subtends the larger solid angle, assuming that the transmembrane voltages and conductivities are the same in both cases. The magnitude of the ECG deflection is directly proportional to the area subtended by the solid angle. 38. In this example, the size of the boundary on the left is clearly greater than that of the one on the right, but the electrode site on the right is closer to the boundary than that of the one on the left. This results in the solid angles being identical, even though the sizes of the boundaries differ. 39. Since the solid angles are identical, the magnitudes of the potentials detected by the electrodes will be identical, even though the actual sizes of the boundaries differ. 40. In this comparison of solid angle geometries, sketch the relative magnitude and polarity of the potential recorded at each site. Assume that the distances from the points to the boundaries are the same. Do changes in the solid angle reflect changes in spatial or non-spatial determinants of the magnitude of the recorded extracellular voltage? 41. The boundary is moving away from P1 and the solid angle is small, so P1 would detect a small negative potential. The boundary is moving toward P2 and the solid angle is large, so you would expect a large positive deflection. Changes in the solid angle reflect changes in spatial determinants of the recorded voltage. 42. The magnitude of the recorded extracellular potential, E, is also influenced by non-spatial factors. The transmembrane voltage gradient, Vm2 minus Vm1, is one of the non-spatial factors. 43. The influence of the transmembrane voltage gradient may be demonstrated in a mass of myocardial tissue, such as the ventricle. In the event of injury or ischemia, the transmembrane voltage in one area, Vm1, is made less negative than normal, while the transmembrane voltage in the other area, Vm2, remains normal. A stationary boundary exists between the injured tissue and the healthy tissue. This example shows the situation in electrical diastole. 44. The magnitude of the recorded voltage is directly proportional to the transmembrane voltage gradient across the boundary, provided the spatial factors and the conductivity term remain unchanged in both areas. 45. The stationary boundary can be eliminated by making the transmembrane voltage identical in both regions. This is accomplished by either depolarizing Vm2 to the same transmembrane voltage as Vm1, or by repolarizing VM1 to the same transmembrane voltage as VM2. The boundary is abolished when VM1 and VM2 are the same. 46. The magnitude of the voltage recorded by the electrocardiogram is also proportional to the conductivity term C sigma, which for the sake of simplicity is also considered a non-spatial factor. The conductivity term consists of sigma I, conductivity within and between cells, and sigma O, extracellular conductivity, A, the cross-sectional area of excitable viable tissue, and S, the total cross-sectional area of tissue, including associated interstitial space. 47. Intercellular conductivity, sigma I, is determined primarily by the low-resistance interconnections between cells called the gap junctions, located at the intercalated disc. 48. A decrease in intercellular conductivity results in a reduced flow of ions across gap junctions, resulting in electrotonic uncoupling. 49. A 50% decrease in intercellular conductivity, sigma I, results in a decrease of about 40% in total conductivity. Therefore, a significant decrease in the extracellularly recorded potential results. 50. The incorporation of the ratio AS in the conductivity equation recognizes that the myocardium is not composed entirely of excitable cardiac muscle cells. Changes in the ratio of viable excitable tissue, A, to the total cross-sectional area, S, can occur when the area contributed by viable cells to the total cross-sectional area decreases, as in cell death. 51. A 50% decrease in the AS ratio results in a decrease of almost 80% in total conductivity, which in turn comparably reduces the ECG voltage recording. 52. Notice the comparison of ECGs for normal cardiac activation and for cardiac activation with reduced conductivity. Given no spatial changes and a constant transmembrane voltage gradient, a decrease in total conductivity will diminish the recorded voltage, but the individual shapes of the ECG will be maintained. 53. The diastolic transmembrane voltage in region VM1 is less negative than in region VM2 due to injury. Which of the listed conditions would eliminate the voltage being recorded at electrode site P? 54. According to our theory, elimination of the transmembrane voltage difference between the two regions eliminates the boundary, so no detectable extracellular potentials exist. Also, cell death and loss of intracellular conductivity across the boundary reduce the total conductivity to zero and eliminate current flow. 55. Your last objective is to be able to describe the application of the distributed dipole layer model and solid angle analysis in interpreting specific electrocardiographic changes, and to state the advantages and limitations of the theory. 56. The final amplitude of the extracellularly recorded voltage depends on spatial and non-spatial factors. The interaction of these factors can be exemplified by observing changes in the electrocardiogram. The specific relationships between cardiac electrical events and the electrocardiogram are presented in other programs in this series. For the purpose of this discussion, you should recognize that the TQ segment corresponds to the resting heart in electrical diastole, the QRS complex to rapid depolarization of the heart, and the ST segment to repolarization during electrical systole. 57. An area of injured tissue establishes a stationary boundary that characteristically shows a TQ segment depression during diastole and an ST segment elevation during systole. Note that the polarity of the transmembrane voltage gradient and orientation of the boundary reverse between diastole and systole. In diastole, the resting intracellular potential of the injured area is less negative than the healthy tissue. At the peak overshoot in systole, the injured area is less positive than the healthy tissue. 58. For the sake of simplicity, let us consider only the diastolic TQ segment depression. Given a constant transmembrane voltage gradient and unaltered conductivities, an increase in the epicardial injury in this case would increase the solid angle. The magnitude of the TQ depression would increase. As we have seen, this is a change in the spatial factor. 59. When the electrode positions and size of epicardial injury, and therefore the solid angle, remain constant, and there is no change in conductivities, an increased transmembrane voltage gradient intensifies the current flow across the boundary, resulting in an increase in the magnitude of the extracellularly recorded TQ segment depression. This is a change in a non-spatial factor. 60. Very different physiological states, such as the spatial change of increased ischemic tissue on the left, or the non-spatial change of an increased transmembrane voltage gradient between healthy and ischemic tissues on the right, can produce identical electrocardiographic alterations. 61. A major advantage of solid angle analysis is that it is valid at all electrode distances from the heart. For example, epicardial, intracavitary, and precordial sites are equally valid electrical perspectives from which to view cardiac activation quantitatively. 62. Consider the use of solid angle theory to predict the calculated change in the magnitude and polarity of the QRS complex at various recording sites as a function of the size of myocardial infarction, in this case, an apical infarction of the left ventricle. As the area of infarction increases, we can predict that the deflections of the QRS complex will decrease in the precordial lead, alter only slightly in the intracavitary lead, and fall dramatically and then increase very slightly in the epicardial lead. These theoretical curves have been tested experimentally and seem to describe the experimental observations quite well. When more complicated two-dimensional or three-dimensional analysis is performed, computer assistance is required for the calculation. 63. You should appreciate that although the solid angles for a cardiac activation wavefront boundary can be visualized rather easily at any instant, the actual calculation of potentials is difficult and is perhaps the greatest practical limitation of solid angle analysis. Mathematical description requires that the contribution from each of an infinite number of dipoles, comprising infinitesimally small portions of each boundary, be summed to interpret the potential recorded at a given electrode site at each point in the cardiac cycle. 64. Further, irregularities in the shape of the thorax and the fact that it is neither a homogeneous nor infinite volume conductor make mathematical description difficult. The following structures and interfaces between these structures may influence the recorded voltage: intracavitary and intravascular blood, the heart and great vessels, the pericardium, lungs, rib cage, muscle, fat, mediastinal structures, skin, electrode paste, and the location and geometry of electrode placement. Non-uniformity and alterations of conductivity between the heart and the recording electrode affect the absolute magnitude rather than the relative distribution of the recorded potential. 65. In this example, there is subepicardial injury of the left ventricular free wall. The situation during electrical diastole is depicted. Given that the transmembrane voltages and conductivities remain constant, and that the orientation of the boundary to the electrode does not change, would a decrease in the area of injury increase or decrease the magnitude of the extracellularly recorded TQ segment depression? Is this a change in spatial or non-spatial determinants of the recorded TQ potential? '66. A decreased area of injury decreases the size of the boundary, the solid angle subtended, and the TQ segment depression. Alteration of the geometry of the boundary is a spatial alteration. A decrease in an area of injury, however, does not necessarily decrease the solid angle. The final effect depends on the relationship of the boundary to the electrode site. 67. Given the same type of subepicardial injury as in the previous slide, and given no change in the electrode position, in the area of the injured tissue, or in conductivities, will the magnitude of the extracellularly recorded diastolic TQ segment depression increase or decrease if the resting transmembrane potential of the uninjured tissue is brought closer to that of the injured tissue? Is this a change in spatial or non-spatial determinants of the recorded potentials? '68. A decrease in the transmembrane voltage gradient between the two areas reduces current flow and therefore decreases the magnitude of the TQ segment depression. Alteration of the transmembrane voltage gradient is a non-spatial alteration. 69. Solid angle analysis provides physiological interpretation of cardiac electrical activity. State two advantages of this approach. What are two practical limitations of the theory? '70. The advantages of solid angle analysis are that it provides quantitative spatial and non-spatial interpretation and that it is valid at all electrode recording sites. The analysis is limited by the difficulty of mathematical description and calculation and by the irregularities of the thorax. '71. We have discussed the electrical activity of the myocardium as described by the distributed dipole layer model and solid angle analysis, the spatial and non-spatial determinants of recorded potentials, and some advantages and limitations of the theory. The post-test begins on the next slide. 72. Sketch this dipole and include several current flow lines and isopotential field lines. State the polarity of the potential detected at points P1, P2, and P3. '73. Point P1 is in the positive field, P2 is in the negative field, and P3 is in the plane of zero potential. 74. This diagram shows a cardiac activation wavefront moving through the left ventricle and 3 electrode recording sites. Indicate the direction of conduction of the wavefront. Label the polarity of potentials recorded at sites P1 and P3, and sketch the relative magnitude and polarity of the ECG recording at P2 as the wavefront approaches, passes, and moves away. 75. The potential recorded at site P1 would be positive, and at P3, negative. As the wavefront approaches P2, the ECG deflection would rise to a peak, drop to zero as the boundary passes, and inscribe a negative deflection and return to zero as the boundary moves away. '76. On the left, a region of myocardium is depolarized due to injury, and on the right, the area of injury is increased. Simultaneous ECG recordings are obtained at a precordial site, P1, and an epicardial site, P2. Assume that transmembrane voltages and conductivities remain constant. On the left, which ECG recording has the greater magnitude, P1 or P2? On the right, after increase in the injured area, which ECG recording, P1 or P2, has the greater magnitude? When the injured area increases, does the precordial, P1, recording increase or decrease in amplitude? When the injured area increases, does the epicardial, P2, recording increase or decrease in amplitude? '77. In the original injury, the epicardial electrode, P2, is nearer the boundary than the precordial electrode, and a larger solid angle is subtended. Hence, the amplitude of the P2 recording is greater than that of P1. After an increase in the injured area, the P2 electrode still subtends a larger solid angle than P1, resulting in a larger ECG recording. When the injured area increases, the solid angle subtended at the precordial site, P1, increases, so the amplitude of the recording would increase. When the injured area increases, the solid angle subtended at the epicardial site, P2, actually decreases in this case, despite an increase in the injured area, so the amplitude of the recording would decrease. This is not always the situation, but illustrates the role of geometric factors in the application of solid angle analysis. '78. Assume that an area of injury depolarizes region VM1 of the left ventricle to a diastolic resting transmembrane voltage of minus 75 millivolts, while the diastolic resting transmembrane voltage in region VM2 remains essentially normal at minus 90 millivolts, and that this results in a diastolic TQ segment depression in the ECG. If hyperkalemia develops, increasing the diastolic resting transmembrane voltages in both regions to minus 70 millivolts, what would be the ultimate effect on the extracellularly recorded TQ potential? Does this represent a change in a spatial or non-spatial factor? '79. The effect of hyperkalemia in equalizing the diastolic resting transmembrane voltages would be to eliminate the stationary boundary, the solid angle, and the TQ segment depression. This represents a change in a non-spatial factor. '80. This completes the presentation of Electrocardiography Fundamental Theory Part 1. For further discussion of these concepts, proceed to Part 2 of Electrocardiography Fundamental Theory. References for additional study are provided at the end of the last program in this series, Electrocardiography Applied Theory Part 2. This program was produced by the Education Office of the American Physiological Society.